Okay, so this lecture is about probabilistic models, and this is kind of like umbrella terms for many methods that explicitly represent the probability distribution, and we do kind of learning and inference with a way that is kind of much more closer to the computation of these probabilistic models. So it becomes clear what I mean. So this is the reason I don't give a one-sentence summary is that because I talked about several different things. So what I talk about today is that we want to have a more focused discussion on models that explicitly represent probabilities. So first we revisit maximum likelihood estimator. Okay. And then after that, we have seen math MLE before. After that, we talk about discriminative versus generative models for classification mostly, and give some examples of generative models. Like one is naive Bayes, and the other is Gaussian discriminant analysis and linear discriminant analysis. So that Gaussian discriminant analysis would be towards the end of this lecture. And then also I talk about Bayesian approach to estimation and inference, so learning and inference. And I talk about maximum a posterior estimation as or map of parameters as a way of approximation of doing a Bayesian inference. So if these don't make much sense, I guess, except the MLE part, that's natural. I mean, we're supposed to learn it. So let's look at maximum likelihood estimation before. We had seen it before in the context of, saying regression with linear models, when we said that the squared error that we get in regression can be seen as having some specific probabilistic model, a Gaussian noise model, and doing maximum likelihood estimation. Do you recall that? And also we had this similar thing for classification. And then we got with some specific model, we got cross entropy loss. So let's try to start or do something simpler. Suppose you have a coin, you have a biased coin, which if you throw it, you either get a tail or head. But your head and the probability of, say, tail is some probability, some theta, which you don't know, and you want to estimate it. So you want to know whether it's 0.5, that probability, which makes it a fair coin or unbiased coin, or it is 0.6 or 0.7 or 0.9, which makes it unfair or biased coin. So, okay, so suppose you flip the coin 100 times, and then lands head and edge 55 times and 40 times tail. So what is the probability that it will come up heads if we flip it again? So that's the question. So what is the answer?
0.55.
0.55 is one answer.
I think that might be, but there's some we don't know. That's the sample estimate of the.
So
not necessarily, but, we don't necessarily have like a probability bounds on that.
Right. So I think if I want to summarize, the answer is that we think it is 0.45, but this is our estimate of it, but it may not be exactly 0.5. And that would be kind of like our sample estimate of it. So this is actually a good point. How did we come up with this 0.45? This is a natural number, natural choice. Like many would say 0.45 is a reasonable number. But how did we come up with that? That's a kind of thing that I want to talk about a little bit more in this part. And just another related question is that suppose we, instead of flipping a coin 100 times, we flip it 2 times, and we get 2 heads and 0 tail. What should our estimate be? Should it be 1 or not? Like if I tell you that, would you say that head, in the future that coin should always become head for sure? Probably wouldn't say that. And why? Why don't you say that? So these are the things that I kind of want to talk a little bit more about. So here what we do is that we define a probabilistic model for how a coin would, the result of a flipping coin would be. And we use we model it as a Bernoulli random variable, which the output is either 0 and 1. And we assume that flips are independent. So this flip and the next flip, they don't have, their results are, their result depends on the model of the coin, but they don't affect each other. So there's a parameter theta, which is the probability of head or tail, one of them, and we want to estimate it. So assume that the observations are independent and identically distributed. We had seen it before. So independent and identical, they have the same distribution, which means that this coin now and after 100 flips, it would still have the same probability of head or tail. It doesn't change. If, for example, the coin is made of something that can be destroyed, I don't know, if you make a cookie and flip a cookie instead of coin, after 100 times, probably you lose your cookie, so you can say head or tail. So that would be an example of not identically distributed. So we had seen likelihood function, which is the density of observed data as a function of the parameter. So in our case, it's a probability of a particular sequence of heads and tails. So under the Bernoulli model with IID observation, let's call xi be the number of heads in ith flip, and x would be either z, 0 or 1. So essentially we're saying that probability of xi being 1 head, for example, condition on theta, the parameter of the coin, would be theta. And of course, the other case, when it is tail, xi equal to 0, the probability would be 1 minus theta, because the probability should sum to 1 in this case. If it was a dice, then we had 6 different cases, and you need more than 1 parameter to describe. So this can be compactly written as probability of xi condition on theta as x to the theta to the power of xi, 1 minus theta to the power of 1 minus xi. And to see why it is the case, just imagine either xi would be 0 or 1. So either this is theta to the power of 1, 1 minus theta to the power of 0. So that term, the second term would be ignored. Or it would be 0 and 1, which the first term would be ignored. So this is just a compact way that simplifies some of our manipulations later. Now the likelihood is after n observation, you have x1 to xn condition on theta. That probability is just because of independence, it would be I from 1 multiplication of I from 1 to n of theta xi 1 minus theta to the power of 1 minus xy. And then if we denote the number of heads by nh and number of tails by nt, then this can be written, we can basically divide this product term to 2 parts, to 10 parts that xi is 1 and parts that 1 minus xi is 1. And then this would be essentially theta to the power of nh times 1 minus theta to the power of number of tails. Just if it's, think about it, it becomes clear why it's the case.
Sorry, I have a question.
Just a second, please. Yes.
Yeah, what does the parameter theta represent? What is the meaning?
That's the probability that if you flip the coin, you observe head.
Okay, thank you.
So yeah, this is the theta is this probability. And as I mentioned in a few lectures before, we usually work with the logarithm of this likelihood because it's numerically much nicer. So we have L of theta, which is log of L theta, which would be, and from here we have NH times log of theta plus NT times log of 1 minus theta. So for example, if we have NH to be 55, NT 45, the likelihood and the log likelihood as a function of theta are, this looks like this. So this is the likelihood. This would be the value, the peak of it would be 55.55. And the same here. But you see that the scale here is like 1 to the power, order of 10 to the power of minus 30. So it's very small and it goes to 0 quite fast. But here, becomes, the range is much nicer. It's order of 200, minus 100 or minus 200. And the structure is kind of much nicer. Even in this range, you have some values that are non-zero. So this makes it for optimization much easier, and numerically everything would be nicer. So what does maximum likelihood estimate is doing is computing the point, the theta, as our estimate, or returns the point in likelihood or log likelihood function that has the maximum value. So it essentially picks this value. The point that is maximized, so here, which would be the same here because log doesn't change the maximizer function. So good values of theta should assign high probability to the, so the idea of maximum likelihood is that a good value of theta should assign high probability to the observed data. This motivates maximum likelihood principle. We're choosing theta that maximize it. What we can do is, of course, we can set the derivative of likelihood function and set it equal to 0. If we can compute, I guess I should change the wording here. We can set the derivative of value function to equal to 0 to find its maximizer. There should be some 0 here. So this is likelihood function, log likelihood. We take derivative of it with respect to theta. So log likelihood was NH times log theta plus NT log of 1 minus theta. So we just derivative with respect to theta would be NH divided times 1 over theta, that's derivative of log, and then minus 1 minus theta. I make it equal to 0 and solve for theta. And if we do it, theta hat of maximum likelihood, our estimate would be the number of heads divided by the total number of flips that we have. So 0.455 in our case. So this is the case. The issue is that if, so this is reasonable, except that, for example, if we have only 2 draws or 2 flips and both of them are heads, that is not impossible. That happens with some reasonable chance. But this maximum likelihood estimate would tell us that our probability should be 1, which is not reasonable. So I get back to this soon to talk about it. Okay, so with this, we can now start talking about our probabilistic models. So first thing that is kind of important part of this lecture is about generative versus discriminative models, and especially classifiers. So what does it mean? So let's go back to classification problem that we have seen many times already. So we have an input X and a classes T, and we want to have a classifier do classification based on X. We say that which of the classes we have. So for example, this is class 1, class 2. We have X, which are features, might be many different things, heights, colors, etc. And the output is class label T equal to 1 or 2. I mean, we can have it different values. So it can be 0 or 1 or -1 or +1. We use different notation depending on the kind of mathematical convenience. So what are the different ways we can do it? So from X to T, what are some of the methods that we have already seen? Just give me a summary of what we have already faced.
Machine, binary classifiers, parameters, decisions.
Okay, so that's good. Yes. Support vector machines. Okay, so support vector machine at a boost. We can use neural networks. All of these methods, there are others here, because logistic regressions, decision trees, KNN, all of them basically define a mapping between input X to T. And actually, we had two different ways of doing it, or the methods that we had seen. Some of them was learning and mapping directly from the space of inputs X to class labels. So for example, if we use decision trees, that was it. Or if we use support vector machine, the output was either class -1 or class +1. What else? So for example, AdaBoost was similar essentially to decision trees. But we had another way to, like logistic regression. So when we use it as classifier, it was a bit different. The output wasn't exactly one of the labels, but it was a bit more. Do you recall what was more?
The probability of it belonging to one of the labels?
Just wait a second because my volume is low. Yes, please.
All right. The probability of it belonging to one of the classes was the output, and then we put a threshold on top of that.
Yes, exactly. So in logistic regression, what we got was the probability of class 1 conditional input. So it was more like this. So we have X, the output was P of T condition on X. So that was the logistic regression. Support vector machine didn't have that. KNN, the way we presented, didn't have this one. But these methods, like either or, they are directly trying to relating input to output. These methods are called discriminative classifiers, which learn a mapping directly from input X to either class label or to probability of output given Y. So this can be T with the same notation as the picture. But there is another way to do it. And do we know if there's another class here? It doesn't sound very loud. There is? Okay.
Hasn't been every week.
Yeah, it's kind of, I guess it's every other week, it's kind of, yeah, maybe I try to do it. Let's hopefully I can talk about it. The other way to think about it is that instead of saying what's the relation between input and output, the class, we say that if we know that this is class elephant, for example, what are the features of a class elephant should look like? So we start from T, the class, and we model generate a probabilistic model on the input. So this would be like this, that we say that we start from a class, T, elephant or bears, and then we say the probability of seeing X condition on T, what is that probability? So it's kind of vice versa. And this is generative model because it's saying that how the data that we observe X's are generated. So a generative model essentially provides a probabilistic model that describing that. So if we have that thing, and you will see that if we have this model, suppose in some way, we can use it for classification through using the Bayes rule. So how does it do? The Bayes rule basically says that the probability of T class condition X is a probability of X condition of T times probability of T divided by P of X. So if we have this model, P of X condition on T, and we also have probability of T, then I have everything for the computation of P of T condition of X. So if I know how to draw elephants, I can use that skill to say one particular sample from that elephant or image, whether it's elephant or bear. So that's a general idea of the generative classifier. Yeah, so I think this might be a good point because to stop. So this is the idea. Now the next, the rest of this lecture, I'm going to talk about how actually to implement it. So for some specific examples of these generative models. And also I'm going to talk about the Bayesian inference of it, which tries to address part of the issue with that MLE example of having, say, 2 or 3 samples and maximum likely estimate giving unreasonable answers. So I guess that's all. I mean, today we want to continue the work on the lecture on probabilistic models. We discussed discriminative approach and probabilistic approach. The idea of discriminative approach is essentially how do I separate the classes? But generative approach is essentially trying to find what does each class look like. So here, if we learn how, for example, P of X condition on T and P of T, then we can use Bayes' rule to compute P of T condition on X. So that's the general approach. What we do, just as an example, let's assume that we want to design a classifier that detects whether a text is spam or not. So we are given a sentence like this, and it says that you get this as an email, and then you want to figure out whether it is spam or not. So one approach is we use something called bag of words feature, which is essentially a dictionary of different words, and we check whether that word exists in that dictionary or not. So for example, the word winner or you exists here somewhere. So that would be a binary feature. Say, for example, it would be 0, 0, 0. So it would be a kind of large, usually very large feature vector which belongs to, say, 100 or 1,000 dimensional space, but it is all binary. So this is just an example. Suppose we want to design a generative classifier or a Bayes classifier that uses the Bayes rule in order to compute the probability that this X is spam or not. So what I'm writing here is general, but keep that example in your mind. So given a feature which is d-dimensional, X from each X has X1 to XT, we want to compute class probability using Bayesian. So what do? We want to compute probability of T condition on X. So this is a probability of class given words, which can be written using Bayes' rule as P of X condition on T. So probability of a word given class, like whether it's spam or not. So if it's spam, probably you see words. Probability of seeing, I don't know, being winner or gift or 1,000, some money, dollar is higher. Then the other is the probability of each class, the probability of one receives spam versus not. So in probably all beginning of internet, early days of internet, there were not many spams, so probability of spam was small. But as it changed, the probability of spams increased. Probably the number of spam emails became larger than meaningful non-spam emails. And then also we have a probability of observing that X, so it's P of X. So is this clear so far? Okay. So each of these terms have a name. Probably you have heard of them. So the first one, the probability of T condition X, is called posterior. this P of X condition on T is called class likelihood. This P of T is called posterior, and P of X is called evidence. So basically what we want to compute is that we want to compute the posterior given the prior information in class likelihood. So another thing that we have is P of X, how we can compute P of X for two-class case. It is easy. I mean, I haven't written down here, but I have it instead here, which is saying that P of X is probability of X when T is equal to 0 times P of T equal to 0 plus P of X when T is equal to 1 times probability of T class label being 1. So to compute P of T of X, what do we need actually is information P of X condition on T and P of T. So if you have that information, you can define the space classifier without any problem. Now the only question is how we can learn these P of X condition on T and P of T. So, so this is generic so far, but after the question of how we model the probabilities and how we learn these things would be, I will give you some specific concrete examples that we can do it. Yes, there is a question.
So are you just saying that we only need to learn P of X given T and P of T given P of X?
That you can compute P of X using this formula, right?
Yeah.
Okay, so the question was essentially how to compute P of X if you have P of X condition T and P of T, or whether that's sufficient.
Yeah, that's reducible.
Yeah. But the other question is that do we actually need it to compute P of X or not for making a classification? And as we will see, maybe we don't need it. Okay, actually, this is a good point. Maybe think about it. So suppose you compute P of T, so you have two classes, say, you compute P of class, let me write it here. So class T equal to 1 condition X, condition X. Suppose this is 0.6, this is 0.4 for simplicity. So what is the right class here? Which class you would say that is more likely to be there? This X should be associated with? 0, okay. When you want to compute, okay, that's perfect. So, so basically you need to compute when you want to do it. Here we compute P of X condition on 0. This would be P of T. This would be of P of X. And then you do the same thing, but P of X 1, P of T is the same, P of X is the same. Sorry, so this is not true. So P of T, oops. So once you do this, and another time, okay. Yeah. So that would be P of 1, P of 0, right? So once you compute you multiply the green things, divide by the green thing. The other times you multiply the orange thing and divide by P of X, which doesn't matter. It's not a function of T. So do you see why we don't need actually to compute P of X? We don't actually need to compute P of X because in either cases, that is the same. So if you want to find which one is actually larger, you just compute the ratio of those, and then P of X would be irrelevant. Yes?
Or we are not classifying.
So this is supervised learning, yes. So this is like still supervised learning that we want to classify something. Right. So, so the question is of what is the evidence and what is prior in practical situation. So prior, I would say, is maybe it's easier to say. It's like for the spam case, prior would be the probability that an email that you receive is a spam or is non-spam. Say if 80% of emails that you receive or comes to your mail server is spam, then that would P of t would be that 0.90 or 0.80. Evidence is the probability that you observe that particular set of bag of words in the space of all possible emails that you receive. You get different bag of words. The probability that you receive that particular, say, this particular count, that is the probability of P of x. Okay, so what we have to do now is essentially just to talk about representation of P of here. So how to represent P of x condition on t and P of t. P of t is not difficult. And then how to learn. And the general, for learning, the general recipe that we have is, in this lecture, is using maximum likelihood estimation. So the first approach is called naive Bayes classifier. It's a very simple generative approach, which makes some assumptions to make some calculations much, and learning and calculations much simpler. So again, the assumption is consider spam and non-spam as a working example. So we have two classes. We have a dictionary of D words, a binary feature that is D-dimensional as the previous section. So nothing changed here. So we need to compute P of x and P of t. If we define a joint distribution of P of t, x1, x2 to xd, this joint distribution of input and output allows us to compute P of t and P of x condition on t. So essentially, if you have a joint distribution of a probability distribution, you know everything about that probability distribution. So how many parameters do we need to specify such a joint distribution? Any idea? So we have d-dimensional x and t equal to 1-dimensional essentially, and each of them takes a value of either 0 or 1. So how many different values do we have? Or can we have? Sorry? D plus 1, no. Like to specify the whole P, you actually need much more.
I mean, probability, it could be anything like a probability density function. It's just a function. So it lives in a
Right. Okay. So just consider that. So the answer was that it's infinite. It can be infinite dimensional, but we have some structure here because P of, you know that x's and t's are binary. So it is not arbitrary. So there is an answer. Yeah. So it's so the other answer is 2 to the power of b plus 1, right? So that's right. If you want to be a bit more detailed, -1, but because you have a constraint that the probability should be sum to 1. But yes, the order is essentially 2 to the power of t. Okay, so that's good. So the dimension, if we want to specify joint distribution over d plus 1 binary variables, we require 2 to the power of d plus 1 minus 1 entries, which can be very large. It can be huge if d, for example, the bag of words, d is in the order of hundreds or thousands, the size of your dictionary. So this is computationally and it's prohibitive. you can't actually represent it on a computer if it is larger than 64, for example. And also it requires a lot of data, like unrealistic amount of data in order to learn that value. So this is the issue of like even learning such a binary variable, like distribution over some binary variables can be very complex. So what we usually do is to define some kind of structure on the distribution that we want to work with. So we say that it has some certain structures, and that certain structure makes that space of the number of parameters that we require to represent that probability distribution much smaller. But also the downside of any structure is that it kind of adds some restriction, right? So restriction, if the restrictions are too restrictive, then we can't represent our distribution accurate enough. So there's a trade-off. And you see what kind of restriction we have in this case of naive Bayes.
Excuse me, I have a question.
Yeah, just a second, please. My volume is low. Okay, yes, please.
Yeah, what do you mean by the parameters needed to specify a distribution?
So so in order to represent a distribution, we need to use some parameters to basically record the values that that distribution can take. So for example, in this case, so
It's the probability mass function.
it's a probability mass function. So if, for example, if we say that this probability, x1 being 1, x2 being 1, so on, we have to represent it by some vector, right? So let's call it vector 1, 1, 1, 1, 1. And then for any other probability, we have another parameter theta that records or represent that distribution. By parameter, I mean those values that we use in order to represent that distribution.
So is parameter in this case t x1 up to xd?
So the parameter here would be theta of all t's and all x's, all possible values that, yeah, so maybe I write it. So the parameters would be theta of t, which x1, x2 to xd. And this can be indexed, this can be either 0 or 1 for all of them, which would be the probability, which again would be the same as probability taking 0 or 1 and x's.
But theta will be one number, right? Because it's one probability.
Yes, so this would be one number, and then you have x's can be either, x's can take 2 to the power of d different values, right?
Oh, okay.
And t can be also taking 2 values. So in total, you have 2 to the power of d plus 1 different probabilities.
Okay, okay.
Okay.
Thank you.
Okay, so we want to, instead of having that joint distribution, which we can take all the possible, or use a parameterization that allows all possible parameters, considers all possible values of x's and t's, we want to make some kind of restrictions. How to do it? One way is something called naive Bayes assumption, which is basically saying that assumes that the word feature xi, each of them from 1 to d, are conditionally independent given the class label t. So this means that if we have xi and xj, or different xi and xj, they are independent when they are conditioned on the class label t. So p of xi, xj condition on t can be written as p of xi condition on t times xj condition on t, when I and j are different. So this is, you know that independence, the definition of it for unconditional variables is that p of, say, or it implies that p of, say, xi, xj can be written as p of xi times P of xj. This is the same concept, but when we are conditional T. So that's the naive Bayes assumption. And the result of it is that we can then write P of T x1 to xt as P of T times P of x1 conditional T, P of x2 conditional T, up to P of xt conditional T. So this is the result of being conditional independence. So now the joint distribution is represented in this way. Now we can talk about how many parameters we need to represent it. So how many parameters do we need? So let's see. So prior probability of class, which is P of T equal to 1, we can write it with parameter pi. So this is a value belonging to R, or actually it's belong only to between 0 and 1. So that's a value between 0 and 1. And the probability of T being equal to 0 is 1 minus pi, because each email is either spam or not spam. So the sum should be 1. Now, suppose, let's think about P of, say, xi conditional T. So that's xi conditional T can take, depending on whether T is positive or not, 0 or 1, we have two cases. Suppose, for now, think about this P of T equal to, T is equal to 0. So we have a probability of xj being equal to 1 when T is equal to 0. Then we have the probability of xj being 0 when T is again 0 is 1 minus the other probability. So we can represent it with some theta of j and T being 0. Now T can be also equal to 1. So we have two parameters actually to describe P of x conditional T. Okay. So how many parameters do we have? We have d variables here. Each of them requires 2 parameters, and then we have 1 parameter for prior. So 2d plus 1 parameters total is required in order to represent this distribution, which, as you see, is much smaller than 2 to the power of d plus 1 that we had before. So this is a much more compact representation of this probability distribution. The downside, of course, is that this is based on this naive Bayes assumption that assumes that we have conditional independence of the word features. Is that true or not? Well, often in practice it is not. Whether how bad it is, how much violation of actual properties of distribution it is, it depends on the problem. But this is a very simple way to kind of like one extreme case that how we can model distribution by making some assumption on the family or the structure of that distribution. Okay, any question now? Yes.
Why do we
Why? Because from this discussion here, either t is equal to 0, and then we have, say, theta, maybe I write it down here. So if t is equal to 0, then we have theta j of 0, let's call it. And if t equal to 1, we have theta j of 1. So this basically means that for each j, each dimension j, we need 2 parameters to represent it. So the question was that why we have two in here, 2D. Just a second. Yes, please.
Yeah, so I had one question about the equation on the top of the slide. Should the left-hand side of this equation also be conditioned on t? Because the left-hand side is just the joint distribution, and on the right-hand side, we suddenly have the conditioned on t.
No, we have also P of t here too.
Oh, okay, yes, you're right. My bad, sorry.
This connection to the model random. That's a good. Okay, so the question is there any connection to Markov random field? That's a good question. So that would be example of graphical model. This is an example of graphical model, but very simple one. So in the sense that all of them are related to, actually I have it something on next slide, that all of them impose some graphical structure, and graphical in the sense of graph. They are related. But then the assumptions of Markov random field or BaseNet in general would be different than this particular based naive base. Yeah, actually this is a good one. So this is exactly like this. So we can represent this distribution graphically using a directed graphical model or a BaseNet. So basically this graph structure, we show it like this, that we have T, and then there is an arrow from T to each of x's, but there is no connection between x1 to x2, for example. So this is essentially saying that this graph structure means that the joint distribution factorizes, and by factorizing I mean can be written into terms, multiplicative terms, in the form that I have on top of this page. That is factors a product of conditional distributions for each variable given its parents. So we have probability of x1 condition on t times x2 condition on t, xd condition on t. These concepts are, so this is intuitively, maybe you can think of it as these edges that connecting t to x as forming some form of causal structure, that t being spanned causes x to have certain distribution. But mathematically, just from having a probability distribution, we can't really infer anything about the causal structure of some variables, essentially. We can say that there's a physical process that given t, it generated x1 in particular way. But with some additional assumption, we can say that. So this is a very simple graphical model, and there are more complex structure, like as already mentioned. So maybe just give an example. How it can be a bit more complicated. For example, we can say that, so we have a t, and then we have x1, so t goes to x1, but x2 can be also depend on both x1 and t. So this is another graphical structure that is more complex than what we have here. So there is a whole field of machine learning called probabilistic graphical model that talks about how we can represent distributions in adding some structure to distribution in the form of these graphical models, and then how we can do learning and inference using them. And we have a course on that, but I'm not going to talk about it more, except this in the context of BaseNet, which is one of the simplest. Okay, so representation we talked about. So we have a very compact representation that only has order of 2 times d number of parameters. Now the question is that how we can do learning. And as I mentioned earlier, the idea here is to learn with a maximum likelihood estimation. So what we do is compute the maximum likelihood of this probability distribution and find the parameters that maximizes the likelihood of the data. So parameters can be, okay, so let's see how it goes. I think you need to probably go through these derivations because I go through them quite fast to get a better idea how actually it works. So, but let's see. So likelihood or log likelihood can be written as summation of a data. So I is the data index from I equal to 1 to n of log of P of Ti and X of Ti. So there's a joint probability. We divide it to two parts. So make it conditional P of Xi conditional Ti times P of Ti. So this is just equality. So, and now I use the properties of, okay, so what I write here now is that I write it as summation of log of P of Ti, where P of Ti is exactly the same as there, but then multiplication of P of Xj, dimension j, of data point I, condition on Ti. So probability that dimension j of this data point, when condition on some word being, some email being spam or not spam, I write it as multiplication of them. So why did I write this? Why could I write this one?
Naive Bayes assumption.
It's because of conditional independence that we have in naive Bayes. So this simplification, this step, is because of this naive Bayes assumption that we have. Okay, then I use the property of log to separate them. So it would become log of multiplication becomes log of P of Ti plus summation over dimensions. So this is from dimension j 1 to d of log of P of Xji condition on Ti. And then I separate them. So this would be this term. The first term would be the log of P of Ti's over summation over data points. And the second one would be log of summation over dimensions, then summation over data points of log of P Xj of data point I conditional P of I. So this is the Bernoulli likelihood for labels. This would be like likelihood for feature Xj. So I think this requires a little bit of thinking, but because each of these probabilities are represented using different, okay, now what we want to do, we want to maximize this log likelihood. So we want to maximize over theta. And theta, remember, is a vector that is 2d plus 1. This is the parameter that represents our naive Bayes structure. When we want to maximize it, now this means that we maximize all of these. And because each of these, like the prior distribution or each of probability of Xj, condition, and T is parameterized by different parameter, we can optimize each of them separately. We can decompose this optimization problem that depends on 2d plus 1 variable to 2d plus 1 small optimization problem. So you may need to think a little bit about this, but that's what we get. So we handle each term separately. For the prior, we have to maximize summation over data points and data points of log of prior. So this is very similar to what we had for coin flip example. So we had used pi for probability of ti or any t being 1. So prior is the same for all data points, of course. So all of these parameters are the same because we have the assumption of the distribution is identical. The distribution of the first sample is the same as the distribution of last sample. So we can write P of Ti as pi of Ti times 1 minus pi to the power of 1 minus Ti. And if you recall, we had it before a few slides ago, that why this is the case. You can just check that this is, you can set t equal to 0 or 1, you see that this would be the case. You either get pi or 1 minus pi, depending on whether t is equal to 1 or 0. So, like likelihood, we just plug in this value there in log. So we get that we have summation of ti log of pi plus summation of 1 minus ti log of 1 minus pi. We want to do maximum likelihood, so we essentially want to maximize this pi such that this term is maximized, which we can do it. And then if we do it, and it's good to verify it, we get that pi hat, our maximum likelihood estimate for prior, would be summation of all TIs that are equal to 1 divided by the total number of data points n. Or in words, it would be the number of spans in the data set, total number of samples in the data set. So our maximum likelihood estimation is intuitive as before. Like if you have data set of, say, 100 emails and 70% of them are spam, you estimate that the prior distribution of observing and spam is 0.7. And that's maximum likelihood estimation that is intuitive. Okay, is this clear? So now we can do the same thing for each of theta j's. The probability of xj, jth dimension of x, condition on t. And t can be either 0 or 1. So it is essentially the same. This is, we recall that we use theta jt to denote p of xji being 1, condition on t. And then we can just do some kind of simple manipulation. We can compute the log likelihood very similar to the previous case. We expand it and then compute the derivative. So I don't go through the equation, each one by one, but what we get is that maximum, after computing the derivative to 0 and solve the equation to find theta of jt, we get that our maximum likelihood estimation of theta jt would be, for t equal to 1, for example, would be the number of words j. Remember, j was words of winner, for example, or u or prize. Number of j appearing in spans, conditional divided by the number of spans in the data set. So this was for the case t equal to 1, which is spam. If t is equal to 0, it would be number of words j that appearing in non-spam emails divided by the total number of non-spams in data set. Okay, so there's a question, I think. So are you referring to this slide? Yeah, I think. So there's a question that can you explain again how we reached line 2 in the previous derivations using naive Bayes assumption. So I believe you're referring to this slide. So this is because I had it here. Yeah, so this is because of conditional assumption, conditional independence assumption, which says that P of, say, xi xj conditional t is equal to p of xi conditional t, p of xj conditional t. So keep that in mind. Now what we have here, just this one essentially would be of p of, I ignore x1, I index. So it would be p of x1 to xt conditional t. So this can be written as p of x1 conditional t to p of xd conditional t, or more compactly, it would be j of xj conditional t. And this is exactly what we have here after you add the index I. Okay. Okay, so learning. So this concludes the learning of naive Bayes. So what do? We essentially just compute this p of theta xj, theta jt's for all possible values of j's and t's. This is computationally easy. Relatively, you have 2d plus 1 parameters. So you just need to count essentially number of words that j appear in spans or non-spans. And for the prior, you only need to compute here count the number of spans in data set divided by total number of samples. So it's a very simple learning procedure. Now we have a maximum likely estimate of the parameters of the model. Now we want to do prediction or inference, which is basically means that inference here means that now you have an X, new data. You want to do inference. You want to compute the probability of T being 0 or 1 conditional on that X. So we need to do Bayes rule. So if we do Bayes rule, we can write it as P of T times P of X conditional T. And then we need to compute the evidence, or we don't actually need to compute evidence, but I'm just writing it here. So it would be summation over all possible class labels. Here, if it's spam or non-spam, it would be only 2 class labels of the same quantity, like P of T prime, P of X conditional T prime. Now, so this is Bayes rule. The first step is just Bayes rule. The second step uses the naive Bayes assumption to simplify that equation. So this means that P of X conditional T, we use conditional independence to get this product of D xj divide conditional T for D different J's. And the same for denominator. So if we need to, if we want to only find what is the most likely T, as is usually the case, you don't want to actually compute the probabilities. You just want to know what is the most likely T. We don't need to compute the denominator. Denominator is just normalizing things to make sure that the probability sum to 1. So this basically means that if we have just the numerator here, that would be enough. So we can write this we can write P of T conditional X, saying that it is proportional to P of T times the conditional probabilities. So this proportional symbol basically says we ignore the denominator because it doesn't really matter for our calculation. So it would be constant. So if we want to find the best class for input X, we compute all these quantities here, P of T, and this one, and then choose a value for all different values of T. In the spam or not spam case, it would be 2. But if you have, say, 10 class classification, you have 10 different values of T. You compute it, then you choose the value with the largest probability or proportion, some quantity that's proportional to probability. Okay, so naive Bayes is a very cheap algorithm. It's easy to learn. computation fast way. Training time is estimate parameters using maximum likelihood estimation. So we compute the number of how each feature, for example, appears with each label in the case of bag of words, and requires only one pass through the data, because by one pass through data, we can count all the possible occurrences that we want. And the test time, it's also cheap. We apply Bayes rule, and it is easy to compute because of the structure of the assumption of naive Bayes. So in general, so this is not always true, but computing Bayes rule or computing these probabilities through Bayes rule is not always computationally easy. So there are a lot of big literature in how to do inference for models like this, for more general probability distributions. But in this case, it is easy. And in the next method that I'm going to talk about. So naive Bayes, the main idea is not the use of their binary random variables, but it is the assumption of conditional independence assumption. So we can, for example, if x's are not binary, but are, say, continuous valued, maybe you can have a Gaussian distribution, normal distribution over x's, and you have similar conditional independent structure, but with Gaussian random variables. And then you can have naive Bayes, Gaussian naive Bayes. So this method is not usually very accurate in practice because of this naive conditional independence assumption that it has. In many cases, it works fine, relatively, but it is not the best way. That's a very simple way. Okay, any quick question?
One question.
Sure, yes.
Should we just renormalize, or like, should we just renormalize those EFT given X's that we get by code to get an actual probability for T?
Yes, so the question is that can we renormalize here to get actual probabilities? Yes, I mean, if you have a finite number of T's, you just sum all those values that you get and divide those values by that sum, and that gives you a probability. And actually, what the denominator is doing is exactly that sum of all those probability would be the value of the denominator. But yes, we can do it. But the problem appears when the number of, say, possible case, the denominator, instead of having a summation, you have integral. So, and in that case, the normalization might be much more complicated because you need to compute the integral, which is computationally costly.
I have a question.
So just wait a second. Was there a question?
Yes. So in what cases do we prefer generative classifiers over discriminative?
Okay, so that's a good question. I don't want to give you a very general answer. If we have, okay, so maybe a good answer is that if we have some knowledge about how the data is generated, then a given class label, how X's might be generated, but we don't know the exact parameters, generative models would be a good idea. Also, if you want to do more complex inference, knowing the whole distribution allows us to do many calculations, which a discriminative approach does not do it. In practice, I'm not sure. It depends on the exact model. Usually, I take it with some grain of salt. Usually, I guess discriminative approaches would be more accurate because they optimize for accuracy than generative approaches. But sometimes the difference would be, especially generative approaches would not work fine if the assumptions that we make are violated. If the assumptions are correct, then they would be actually performing very well.
Okay, thank you.
Yeah.
Sometimes you want to create fake data with the generative model.
Yeah.
Or models in terms of task or multiple relations, etc. Or you want to study the structure of the data set in some way. And then, so there are reasons for generative models that are.
Yeah, so yeah. Okay, thank you. Yes, that's right. But sometimes you want to generate data from the generative model, new data. That's true. So studying the structure of data, I'm going to talk about it later, a little bit in unsupervised learning. Okay, so let's talk about Bayesian parameter estimation. So this is a kind of like a not related topic, but different from this generative versus discriminative classifiers. After I talk about this, we go back to one other example of generative classes. But maybe we can have a break actually. So I think I looked at the time. So now it's 12:08. Maybe we can start 12:12, like in 4 minutes. Okay, so let's get started. So maybe before starting this part, there's a question that why the parameter on the chat saying that why the parameter counts before naive base is 2 to the power of something minus 1. Where does that term minus 1 comes from? So that the answer is that because we know that this is a probability distribution, you have one constraint that the summation of all the parameters or all the probabilities should be 1. And that's why that minus 1 comes. For example, just simplest case, like a random variable that takes binary values, the probability of, so it takes either 0 or 1, but we only have one parameter that require to explain it. Because the other probability of, say, 0 would be 1 minus p. Okay, so let's talk about Bayesian parameter estimation. Where's my screen? So Bayesian parameter estimation. So we talked about maximum likelihood estimation throughout this lecture so far and before. One issue that we have already encountered or mentioned was the case that the number of data points is very few. For example, we flip the coin twice and we get head both times. Then maximum likelihood estimation, which says that this is the estimate that probability of being head is NH number of heads divided by heads plus tail. So it would be 2 divided by 2 plus 0, which is 1. This is this is unreasonable. I mean, having 2 heads, even for a fair coin, is not unusual. There's small probability, but not actually too small. But saying that distribution, with certainty, saying that probability of having tail or head is 1 is just a bit too much. So this is an issue that is called data sparsity, that we don't have enough data to have high confidence estimate of our parameters. This happens when we don't have enough data. So how to mitigate this approach or this issue is by using, one approach is by using Bayesian approach for estimation and inference. And I want to talk a little bit about Bayesian approach. So here the idea is that in maximum likelihood estimation, what we assume is that there is observations that we see are random variables, but the parameters that described as those observations are not. So there is this theta, the true theta, that we don't know what it is. This is the probability of having head, for example, in the coin example. And we are observing some samples coming from that distribution, or distribution that is specified by theta. So we observe head, tail, something like that. So this is actually, you can think of it as the kind of the idea behind frequentist approach to statistics and probability, that assume that there is the truth somewhere. We don't observe the truth, but we have samples from that truth, and we want to estimate that. And maximum likelihood estimation would be a kind of a very well-known approach in frequentist statistics to estimate the parameters. The Bayesian approach, however, assumes that the parameters itself are random variable, and now which means that we can have a prior distribution over those random variables as well. So what does it mean? Theta, which is the parameter of, say, coin, has a distribution, and that distribution is specified by another parameter, beta. And here the beta, for example, is real value, so there's nothing random about this. But it induces distribution over theta, and then we have samples from one of the thetas that have been samples from beta. So this might be a bit confusing, but let's see how it looks like. So to define a Bayesian model, we need to specify two distributions. One is a prior distribution over parameters, P of theta, which encodes a belief about the parameter before observing the data. And the other is the likelihood of data conditioning theta. So this is the same, this part is the same as what we had in maximum likelihood. But this part that we have a prior distribution over parameters is the kind of the new thing in the Bayesian approach, Bayesian inference and estimation. Yes?
The same as the maximum likelihood that we have for would that be a random correlation?
Right, yes. So for one specific theta, it would be the same. Like if we fix theta, then it would be similar to what we had in maximum likelihood. But theta is not fixed, so we have, it can take different values as you see. So this basically means that, okay, if we can do Bayes rule and update our belief about the parameters. So what we have here is that we want to compute P of theta, condition on data that we have observed. So this means that we need to consider the probability, that its probability would be probability of data, D, for one specific theta, which is a vector of parameters, times the prior distribution, prior that we have over that parameter theta. And this P of theta can, of course, theta can take different values. So for different thetas, we have different priors. And then for normalization, we have the same thing as before, that we have an integration now over theta primes. I use different theta. I use theta prime to denote that that's different from the theta that we have here. So this would be the normalizing factor would be P of theta prime times P of data conditional theta prime of D of theta prime. So I use integral here instead of summation because in general theta is a real value parameter. It's a parameter that we use, for example, to describe the probability of something happening, like coin being head. So that takes a value between 0 and 1, right, for the coin case. So that's why we need to have integral over it instead of having summation, which would be more appropriate if you have a finite or a countable number of values. So, and as before, we don't usually compute the denominators explicitly, and in general, it is computationally intractable for general models. So one thing that I kind of want to mention, or at least briefly mention, is that there is some difference between interpretation of probability according to a Bayesian and a frequentist. Frequentist would be the person who would become doing maximum likelihood estimation. And Bayesian would be the person who does set a prior over your parameters and use this Bayes rule computation in order to compute a probability. There's a lot of debate. Okay, it's a bit difficult to say what exactly it is, but maybe this summary that I have is accurate enough, but it's not. It doesn't summarize the whole picture. So for the frequentist, the probability is essentially a number of times that some statement is true when we observe a lot of samples. So what does it mean? For example, we say that the probability of a coin being head is 0.6, for example. It's a biased head, means that if we flip the head for many times, like infinite times, 60% of times, it becomes head. So that's the meaning of probability. If we do an event many times, that statement, head is, coin becomes head, is true, is 60%. For Bayesian, there are very different beliefs or different versions of Bayesian. But one version of it is that probability is about a belief, our belief about the truth of statement. And it does not have anything to do with some external reality. So it doesn't say that if we do things many times, that's what we have, that's what happened. But it says that if we believe that, that's how the world works. So there's a bit, this Bayesian interpretation that I mentioned is more subjective. Let's talk about the beliefs and not the real world. But this is usually called subjective Bayesian. And if you're more interested, I think there is a book called A Probability or Probability Theory by E.T. James that promotes this viewpoint. So we don't want to get into this. Really, for practical cases, we can consider both interpretation more or less the same. But I just want to say that there's a lot of debate which one is actually the more is a better interpretation. And probably because there are two different interpretations, none of them is better. Okay, so let's talk about our coin example. We know the likelihood function. So likelihood function was probability of data, condition on some theta. So it would be theta to the power of number of heads times 1 minus theta to the power of number of tails. So this is easy. So if theta is fixed, we can compute it. But we need to compute the prior, this distribution over parameters theta. And there are different ways to specify that. So this is essentially, we want to say about our belief about what theta is, theta should be before actually seeing the data points. So one way is to say that we don't have any preference for any theta. Okay, before that, what is the range of values that theta can take? Right, so 0, 1. So theta is between 0 and 1. If it is 0.5, it is the exact value. Sorry, it's an unbiased coin. If it is 0.1 or 0.9, it's a very biased coin. So essentially, we have something like this. We need to specify a distribution of the thetas, which may look in a okay, so this is the value of 1, this is the value of 0. You have to specify a distribution here. One way to specify it is saying that we don't have any preference over any particular value of theta. All of them are possible. So we don't want to put any preference over any theta. This is called uninformative prior, which assumes as little as possible about distribution. And then if it is we have this kind of assumption, we don't want to be informative, we want to be uninformative, then a reasonable choice, the choice here would be a uniform prior, which is here, like the value, the density there is all 1 for the values between 0 and 1, and of course, because outside it would be 0. But then this has a problem. And the problem is that if most coins that we have seen before in this world, they're more or less an unbiased coins. So the probability is probably 0.5 or maybe 0.4 or 0.6. It's more likely to have a coin that has that probability around there instead of a coin that has the probability of 0.95. So we want to give a preference over values that we believe are more likely. So this suggests that maybe we shouldn't use an uninformative prior, a uniform distribution here, but something that is more concentrated around value of 0.5. One distribution, so we need to specify distribution. One reasonable distribution for doing this is called beta distribution, which is specified like this. So it says that P of theta is specified by some constant, times theta to the power of a minus 1, 1 minus theta to the power of b minus 1. And maybe it's good to take a look at it. So A and B here are the parameters of this distribution. So by specifying A and B, we can say what this distribution should look like. This gamma is the gamma function, and doesn't matter for our kid. In this study, or in this lecture, this has this property of gamma of n for integer valued n is similar to factorial of n minus 1. So that has the property of it, but it is defined for values that are non-integer too. So we can have gamma of 3.5, for example. But this constant, this is gamma, doesn't really matter. So using the notation for proportionality, we can ignore the normalization constant and say that P of theta is proportional to theta to the power of a minus 1, 1 minus theta, b minus 1. So let's see how it looks like. So this figure just shows this probability distribution for different cases. So the green one, the green curve, is when A and B are equal to 1. So this is this one. So it becomes uniform. So it specifies, if you choose A and B equal to 1, it specifies a uniform distribution. Another value, for example, is A5B5. This looks like this red curve, which basically is concentrated around 0.5, but it's concentrated around 0.5, and the probability as we go towards 0 or toward 1 decreases. Another value, for example, is this purple one. A is 200, A, B is 100. It looks like this, that density, that is concentrated around a value of 2/3, but you see that the probability goes to 0 very fast as we move away from it. So some properties of this distribution that is good to know is that one is that the expectation of that theta is A divided by A plus B. So when A and B are equal, so the expectation of it would be 0.5. So the other is the distribution gets more peaked when A and B are large. We see it in the purple curve. And uniform distribution is the case that A and B are equal to 1. So this is a distribution that is very flexible, or flexible enough for our purposes to incorporate our prior belief about theta. So we use this beta distribution as a prior for the Bernoulli distribution. Okay, so let's compute the posterior. So posterior is P of theta condition and D. It's proportional to prior times the likelihood. So the prior part is the first term. So this is the prior part from the beta distribution, and the likelihood is theta to the power of number of heads, 1 minus theta to the power of nt, which we saw it before. And if you kind of rearrange these things, we get something like it is equal to theta to the power of theta to the power of a minus 1 plus number of heads times b minus 1 time plus number of theta, tails. So this is one thing that is noticeable here. This is essentially a beta distribution, but with the new parameters. Remember that the form of beta distribution was like this. Theta to the power of something, a minus 1, 1 minus theta to the power of b minus 1. So what we have here is essentially the same, but this is like new a prime and new b prime. So this means that we have a new beta distribution when this is the a parameter of it, or a prime parameter of it, and this is the b prime parameter of it. And we can compute the posterior expectation of it from this formula that we have here, that expectation of theta is a divided by a plus b. So we just now replace it with a prime and b prime. And what we get is expectation of theta condition of b is nh plus a divided by number of heads, number of tails, or total number of data points, plus a and b. So this gives an interpretation of what a and b are doing. We can think of it as some form of pseudo counts. So these are not actual counts of coins that we have observed in data, but they are added to our estimate as if we had seen those number of heads and b number of tails before even seeing the any data. So there was a question, I think. Yeah. A and B are the parameters. So the question is, what are A and B? So A and B are the parameters of the beta distribution that we want to specify. The beta distribution, it has some parameters, 2 parameters in it, actually, and then those are A and B. And they affect the distribution in this way, that you see A, B appears in these exponents. And the way that it changes the shape of distribution is specified on this figure.
So
Sorry, can you say a bit louder? Yeah. Yes, yeah. If I heard it correctly. Okay, so there is a question what posterior means. So posterior distribution, okay, so there's a question, what does posterior mean? Posterior means essentially is this distribution. This is a distribution that we see after, okay, so how it works is like this, that we have some prior belief about the parameters of our model. Prior means that before seeing the data. Then we observe the data, so we observe D, and now we have to take that information that we get into account in order to update our belief about the parameters. This updated belief is called posterior distribution, the distribution that we get to after observing the data. So there is a question So there's a question. Yeah. For Ahmed.
So yes, so my question was, does the uninformative prior make it so that our process kind of degenerates to the frequentist approach?
So I guess in this case, yes, I think usually the idea is that, I mean, I guess the motivation is not just make it exact the same as frequentist approach. In many cases, it may become the same as the maximum likelihood estimate. Like if we have a, say, uniform prior of a, if you use uniform distribution as a prior, the prior doesn't matter, so it becomes like maximum likelihood estimation. But the motivation is essentially just not to impose any belief into our our Bayesian calculation.
Yes. So, like, okay, I get the motivation. My problem is with another part, is that in this particular distribution that we talked about, A equals B equals 1 would correspond to a uniform distribution. Is that correct? For the beta distribution. Okay. So, and that would mean an uninformative prior, meaning that we have no preference for anything.
Yes, but it wouldn't be exactly the same as...
Yes, exactly. So that was it was kind of counterintuitive. It seems that A equals B equals 0 would degenerate to the frequentist.
Right, yeah. But I guess the answer is that the goal is not to make it a frequentist approach in general.
Okay, and would it be kind of legitimate? Would it be a good distribution if we put A equals B equals 0? Would the beta distribution still be meaningful? What would it correspond to?
I'm not sure it makes sense in that case. I'm not sure.
Okay, thanks.
Okay, but yeah, I guess that's a good question. Yeah, because if it becomes uniform distribution, then it should become maximum likelihood estimation. So we only have likelihood in the Pareto, so it should be the same as maximum likelihood. Okay, so that's, I need to check maybe, but I'm not sure. I will check it. Maybe there is -1 and -2 here.
Yeah, that would make much more sense. Yeah.
Let's see. Maybe it was a typo. I had some. No, it's not. Okay, I have to check that. But yeah, that's a good point. But in general, the idea is not making it frequentists. But yeah, if uniform should in this case becomes the same as MLE. But why it doesn't, I have to check it. That's a good point.
Thank you.
Okay. Okay, so let's see how it looks like if you want to do Bayesian inference for a coin flip example. So here, basically, in each figure, I'm showing both the prior likelihood function and posterior. So prior is the blue curve. It's prior. Likelihood is likelihood that we get for the data that we have. And here the data assume that we are in the small data setting, so that we have to observe 2 heads and no tail. So in that case, the maximum of likelihood is appearing at this point. So maximum likelihood estimate would say that the theta should be equal to 1 because that's a maximizer of the likelihood. But then in Bayesian inference, we have both, we multiply the likelihood by prior. So the multiplication looks like this red curve, and that would be our posterior. So this is essentially distribution of all possible thetas. So Bayesian inference doesn't say which theta is the correct theta. It says what are the possible distributions, or for each possible theta, what are the probabilities of that being the true value. And you see that the probability is concentrated around here. but even for small values, we have some non-zero probability. So we now suppose we have a large data setting, 55 heads, 45 tails. So prior is the same as before, but let's look at the likelihood and posterior. So it's difficult to see. I guess if you said there are two curves that are very matched to each other. So one is likelihood, the green one is likelihood, red one is posterior. So a small difference here, which basically means that prior, when we have enough data points, doesn't change actually our result. The distribution of the likelihood is almost the same as the posterior. So this indicates that, or kind of suggests that if we have a prior, if we have a lot of data points, the choice of prior doesn't matter much as long as it is reasonable. But if we have a few data points, the choice of prior matters a lot. So we can say that data overwhelms the prior when we have enough data. Okay, so now we have a posterior. What should we do by posterior? Is there a question there? Or no. So what do we want to do with posterior? Posterior tells us what is the distribution of our parameters given this data that we have, and also considering the prior belief that we had. But if we have that distribution, maybe we want to ask a question like, what is the probability that in the future, if I flip a coin, the coin become tail, for example? That was the goal of this model, essentially. In maximum likelihood, when we had, say, some values, it would say that our estimate is that it is like the probability of another future draw of that coin would be like 0.6, for example. We want to do the same thing given this new information, this distribution of our parameters. So this is called posterior predictive distribution. So the word is predictive, and it's a prediction, or it's a distribution of a future observables, or what we observe, given the past observations. So we want to predict the future probability of tail condition on in the past we have seen 2 tails, 0 head, for example. So that's this posterior predictive distribution is same, and this is essentially P of D prime condition on D in general. D prime is the data in the future. D is the data that we have seen so far. So we can just do marginalization. We can think of it like this, that we have probability of D prime condition on theta. What's for some particular theta, what is the probability that we observe a head next? But we have theta is not one single value, but actually it has a distribution. And its distribution is P of theta condition on D. So distribution of P of theta condition on D is our posterior distribution. So posterior of the parameters, we integrate all these values. So there is integration involved in order to get to this value of posterior predictive distribution. In general, this is not easy, but for the coin flip example, we can do it. So how does it look like? Probability of x prime, the next x, being head given data is, again, P of x prime being head condition of some theta times probability of theta condition on the posterior. And this distribution, okay, so what is this value? Probability of x prime being head condition on theta is theta, because theta was defined as probability of seeing a head. And now the probability, the posterior distribution is the beta distribution with parameter number of heads plus A and number of tails plus B. So that's the posterior distribution, which we had it before from here. So if we do that, so this is essentially, we have a beta distribution multiplied by theta. So this is essentially the expectation of that beta distribution. So expectation is probability of something times the value of that something. So this means that we are actually computing expectation of theta when the distribution is this beta distribution. And we had that formula, what is the expectation of beta distribution, which is nh plus 1 divided by nh plus nt plus a plus b. So this is the probability that the next draw, coin flip, would be head, condition on these data that we had seen before, and it depends on our prior belief, which is encoded by N and B. Okay, question, how confusing this is? I feel that it might be a bit confusing. Or are you following? Yeah, more or less. Okay, that more or less is good enough. Okay, so how much we have time? Okay, so just this is another example. Maybe I skip it.
Sorry, I have a question.
There's a question here, this question which is not obvious. You have to think about it, but it is, I guess, actually a good thing to think about.
I have a question.
So let's compare MLE and Bayesian estimation. Bayesian approach usually deals better compared to with data sparsity when we don't have enough data compared to MLE. The Bayesian approach allows us to incorporate prior knowledge in some cases, but the choice of prior is not always easy. It's like in this case, we could encode it in form of beta distribution. But in general, when people want to do Bayesian inference, they usually choose this prior distribution, which allows us to do computation easily. But it doesn't mean that actually that prior distribution is the right way to encode our beliefs about some phenomena. And sometimes we don't actually have much prior belief about anything. So this is one of the criticism of Bayesian approach from a frequentist that may say that, okay, how did you get your prior belief? And of course, Bayesians would have some answers. So one question that might be actually good for you to think is that, is there any way that we can incorporate our prior belief, some form of prior knowledge in maximum likelihood estimation?
We can add pseudo counts.
Yes.
Just by doing some data along like based on whatever you think it is, and likely you think it is.
Okay. So the answer was that we can somehow generate some fake data and maybe add it to our data set or something like that. So that's one approach, but there is, I think, somehow a more principled approach that we had seen in lecture on linear models, but we didn't really talk about it in form of MLE or how incorporating prior. Yeah, I guess maybe I mentioned it. Maybe think about it and let's see what we had. It's somehow related to, we want to put some form of, we talked about it in form of constraint. We want to put some constraint on our parameters. Our prior belief that some constraints are more meaningful than others. So there is a question here. Yes. Farza?
Yes, yes. So I wanted to ask, why do we need to compute posterior predictive distribution when we have posterior distribution? And in the end, they like is it the same thing, or when do we compute what?
So posterior predictive distribution is about predictions. So it's about head or tail, for example. Posterior distribution is over parameters of that probability distribution, and they're not always the same. So, for example, predicting that next coin would be, next draw of a coin would be head is not exactly about, it's not exactly the same as, it's related, but it's not exactly the same as the probability of the parameters of a coin being certain values. So that's the thing. And I guess in this case, like the relation is very clear because, or very direct. But in general, in some cases, in other cases, the relation is not necessarily as direct. So maybe one line summary is that one is about data, probability of data happening. The other is about the probability of parameter. And parameter and data are not necessarily the same, semantically the same thing.
Okay, thanks. That makes sense.
Okay, so so that's part of the comparison. So maximum likelihood estimation is usually we formulate as an optimization problem. We want to optimize a parameter that maximizes the likelihood. But Bayesian approach is usually in the form of an integration. We need to take expectations here. So you see that we have this expectation here that needs to integrate over all posterior distributions in order to get to us the probabilities. And usually integration is more difficult than optimization. So usually doing maximum likelihood estimation is much easier in practice because we can just do gradient descent. And there are also the packages that does this automatic differentiation. I think you have seen it in your tutorial in PyTorch, that essentially you can let the package does most of the difficult part. There are packages for Bayesian inference and computing these inference integrations that is required in Bayesian inference, but they are, I think, less common and less developed compared to this automatic differentiation. Though, of course, it is changing a lot. But the problem, I think, usually is more, optimization is usually more easier problem compared to integration. So that's why not everyone does Bayesian inference. But in many methods, we have maximum likelihood or a variance of it. Okay, so there is something that is in between full Bayesian approach and maximum likelihood, and that is called maximum a posteriori estimation or MAP estimation. MAP estimation is essentially saying that let's look at the posterior, but instead of just considering the whole distribution of posterior, find the point that maximizes the posterior. So this was the posterior. Instead of using all its value and does the integration, we can look at this point that maximizes it, so whatever value it is, and say that this is our estimate. So we provide one point as our estimate instead of having the whole distribution. So this is an approximation of the full Bayesian estimation and inference because it only finds one parameter instead of having a probability distribution over our parameter. So this is not as powerful, but this is brings some benefits of Bayesian approach into maximum likelihood estimation. So in this case, for example, maximum likelihood estimation, it says that we have to choose here, which is unreasonable value. But here, choosing this value, the peak of that posterior, is reasonable. So this converts a Bayesian parameter estimation into maximization problem. So we have theta of maximum a posteriori is argmax of over theta of posterior. We can write it as, it's the same as argmax of P of theta and D, because the normalizer, which is P of D, doesn't matter. So we can use it, we can write it as P of theta times P of D condition on theta. And then this is equivalent, taking log of the objective doesn't change anything. So we can write it as P of log of P of theta plus log of P of D condition at theta. So this was the term that we had for MLE, but this is the new term that is coming from the prior. And we can do this calculation for our coin flip example. So P of theta condition on D would be proportional to this term. So the log of it, you can verify that it would become some constant plus this term times log of theta plus this other term times log of 1 minus theta. We find the take derivative with respect to theta, set it equal to 0. And if we solve it, we get a value like this. So let's see what the formula says or looks like for the two cases when we have few number of data points and we have a lot of data points. For maximum likelihood estimation, for the Bayesian approach, expectation of the posterior distribution, and the map approach. So the formulas are similar. I mean, this is MLE. This is full Bayesian approach. This is the maximum a posteriori approach. The values, if you compute it, it gives 1, probability of head is 1, which is not meaningful. But for the other two approaches, it gives more reasonable values. If the number of data points is large, all of them are more or less giving the same value. So there are basically data overwhelms here, the prior. So yeah, I guess that's what.
If you had more data set, right, if you have higher dimensional set of variables in high distribution,
Yes.
especially if you have multiple data in multiple dimensions, then it would take a lot more data to overwhelm that, right?
I think so, yes. If it's so, I believe so. Yes, that would be the case. But I'm not sure what would be. I mean, there are results showing that what is the rate that posterior converges to, say, certain points. And I can't remember what is the dependence of convergence rate and dimension. I believe that would be the case, that if dimension is larger, convergence would be slower, but I don't remember what exactly would be the rate. But it seems intuitive that if dimension is higher, it takes longer, but I'm not 100% sure. Okay, so maybe we should finish. Okay, I didn't finish this lecture, so Gaussian discriminant analysis is another example of generative model like naive Bayes, but in a different forms of assumptions. So just one question, are you okay? Probably I have a poll, but are you okay if you have some extra lectures on tutorial or on at some other point in time? Or do you prefer, one of the possibilities is I just record the lecture without the class? First one. Okay. Okay. Okay, so I can do that. The only problem is that I've already booked things for tutorial. So there are material for tutorial, so we'll see what we do. And I guess, the other thing is that whether you want to learn about statistical learning theory or not, if we don't want that, so the last lecture would be reinforcement learning, and I guess we are on time. We don't need to use any extra text. But if I want to have that extra that extra lecture, probably I need to use something else. Okay, I guess we should go. Okay, maybe I ask it on Piazza to see what is the general opinion. Okay, have a good day.